throughout computing. So what is an array actually? Julia allows us to think of arrays in a more general way than you might be used to. You're probably used to thinking about cells arranged one after another in memory, where all the cells are the same size, they contain the same type of information, and they're just stored consecutively. But from a user's point of view, what we actually care about is that the array looks like that. It feels like that. In particular, well, we want to index into the array, so each element should have an integer index from 1 to some number n. The element at some position I, we want to access using a particular syntax, which is a square brackets I, and we want to perhaps modify that element with something like a square brackets I equals a value, if the array is a mutable object. And an array should also have a size. We should know how big the array is in memory. And so Julia provides an abstraction of an array, which is called abstract array. It's an abstract type, and we're going to be able to define new types of array. In other words, new objects in Julia that behave as if they were arrays, but they can be stored in a different way in memory. So how does Julia actually do indexing? Suppose we define a vector called array, R, which is just 3 elements in the usual way. We know that we can index into that using square brackets. R square brackets 2 gives me the second value in the array, because we know that in Julia we usually start indexing arrays at 1. The first item in the array is indexed as element number 1. So what is actually going on when we do this array 2? We can see this by looking at the lowered form of the syntax, which is just a more internal representation that Julia uses. And what we see is that it's actually calling a function called getIndex, which is defined in base. Array square brackets 2 is just syntactic sugar for getIndex of array comma 2. In other words, it's just a way of writing that in a nicer way that's easier for us to write, but Julia just immediately translates that syntax into this function call. And so if we actually extend the function getIndex on our array type, we can also use this same syntax. Let's do an example. We're going to actually do a zero-based vector. In other words, a vector which we can index starting at 0. So there are many, many discussions on the internet about whether zero-based indexing is better or is one-based indexing better. And of course the answer is that these discussions are completely pointless because neither is actually better. Sometimes you want zero-based and sometimes you want one-based indexing. It depends on the application. And so Julia has a pretty general package called offsetarrays.jl where you are actually able to use any type of indexing. We're just going to implement the simplest possible case, which is a zero-based vector. Let's define a type called zeroFirstVector. It'll be an abstract type which can hold any type t inside. So the elements of this vector can be any type t. And it will be a subtype of this abstract vector type with parameter t. And inside there's just going to be a normal vector, a field called array, which is of type vector with elements of type t inside. What do we need to do? We need to define getIndex on our object. So we need to extend the getIndex function from base Julia. So when we pass in a vector which is of type zeroFirstVector, we'll give it an index which is an integer. And what will we do? Well, we'll just add 1 to the index to take account of the fact that I'm storing inside a standard Julia vector that I need to index starting at 1. But I want my indices to go from 0. And so when my index I is 0, well, I need to access the first element, the element number 1 of the standard vector. It turns out that I actually need to extend other functions, which are size, how long is the array, and axes, where does the array start and where does it array end. And once I do that, I now have a working zero vector. So I just have 3 lines of code, and suddenly I can use zero-based indexing as well. Let's just define this Z array, which is a zeroFirstVector with this array inside, 1, 3, 4, and now I'm just able to index Z array at element 0, and it gives me the first element, the 0th element if you are using zero-based indexing. In a similar way, when I modify an index, so if I do array number 2, index 2, and I want to set that equal to 3, I want to assign the value 3 to that index, this is calling another function in base called setIndexBang. Bang because it modifies its argument. It's going to modify the array at index number 2, and it's going to set it equal to the value 3. And so it's going to call this setIndexBang function, modifying this object array at index 2, which goes last, and make it 3. And so we just extend that to do exactly this with our index transformation in the same way that we did for getIndex. And when we do that, we can now modify the 0th element of the array to be 55, and here is the result. And we see that indeed the first element was modified. Since we have made our type a subtype of abstract array, it turns out that Julia gives us some added bonuses. For example, now we can index Z array with a range. So before we only indexed with an integer, and that's all we actually defined, but Julia is allowing us to index with a range. Another thing we can do is to look at Z array indexed by a vector. So we're actually putting in a vector, and we'll take the elements of the array at these indices. So at indices 2, then 1, then 0. So effectively we're reversing the array, and we see that indeed we get the result in reverse order. And then we can assign to the array using indices or using vectors. And this all comes for free once we've defined the previous functions. Other functions also work automatically. For example, there's a sort bang function, which takes in a vector and sorts it. And now we see that this function actually already works on our zero-based vector and sorts the vector in place. We've already seen some other examples of abstract arrays in the course. For example, ranges are abstract arrays. So let's define this range from 53 to 83. And we see that size is defined, that's the number of elements in this range, and we can access elements using standard indexing. So what is the type of that range? It's this unit range type, and if we look at supertypes of unit range, we see there's a whole hierarchy of types, but in the end, unit range is a subtype of abstract array. So the definition of unit range is that it's a subtype of abstract array, it only stores the first and last elements, and getIndex is defined for that type to extract the correct element of the array. And finally, let's look at what happens if we reshape that. So let's start with a unit range, and we'll reshape it into a matrix. So there's this reshape function, we give it the size of the matrix that we want, and what we get is something called a reshaped array back. And so you can see that the type of that object is actually a bit complicated, because basically what it's saying is that this is a type of array, so it's a reshaped array with 2 dimensions which stores integers inside, but underlying that array there is a unit range, right? The underlying sort of parent array of that reshaped array is actually stored in a unit range. And again, a reshaped array is a subtype of abstract array. Finally, we can look at the transpose. So what happens if we now transpose this reshaped array? We get a transpose with this reshaped array inside. So it's a wrapper, it's a layer on top, but the underlying data is still my original unit range. For example, when I do getIndex on this transposed object, what does it do? Well, I pass in the transpose object and indices I and j, and all it does is take the parent array that's stored inside the transpose object and indexes that at j and I. In other words, it swaps the indices round to give me the transpose effect. So in conclusion, let's go back to the question, what is an array really? What is an array actually? And the answer is that it's actually something that looks like an array, it behaves like an array in the sense that I can index into it, but also it behaves like an array in the sense that actually any of these arrays that we've been looking at, I could, if I wanted, materialize them. So I could, if I wanted, make an actual usual array with all of the boxes stored consecutively in memory, and it would behave in exactly the same way. But Julia provides this generic mechanism so that we can define these new types which are more convenient or store data in a more efficient way in memory and behave in the same way as an array, such that your program will not actually be able to tell the difference between one and the other.